Okay, then again, thank you very much for the introduction, and also to the organizers. Thanks a lot for the opportunity to give a talk in this very interesting conference. So the topic today is phase contrast X-ray tomography. And so what I'll talk today about is some results of a long-term collaboration with Tim Zaldit. He is an experimental physicist in Göttingen, and with Simon Maretzke, now Simon Huhn, who is a former very good PhD student. He's now working in industry, unfortunately for us. Okay, so here's the plan of my talk. I'll start with an introduction of this imaging methodology. So basically the mathematical modeling, and then I'll show some uniqueness and stability results, address the issue of finite detectors, and give some reconstruction and discuss the results and give some outlook on future and ongoing work. Okay, so the basic aim of phase contrast tomography is to image not the absorption coefficient, which is the imaginary part of a refractive index as in standard CT, but the real part of the refractive index. And so why should we do that? Well, main reason is that for living tissue at X-ray frequencies, you have a much higher contrast in the real part than in the imaginary part. And I mean, ideally, of course, we would like to image both the real part and the imaginary part. Then we just get more information on the sample. Okay, so how does this work? I mean, as in CT, what we measure is line integrals through the sample along straight lines. So the problem that arises is that for X-rays, one can only measure intensity, but not phases. And so if you look at such a line integral, you see that the imaginary part of n only has an effect on the phase of this. Yeah, actually you measure the exponential of line integrals, so then it only has an influence on the phase of this measured data, and it leaves the absolute value the same. So actually, from these type of measurements, we have no information at all on the real part of n, but only on the imaginary part of n. Okay, so that's why if we want to get some information on the real part of n, we need to modify the measurement setup to be able to somehow get additional information on the phase of these line integrals, or the exponential of these line integrals. There are different techniques how to do this. Interferometric techniques that were also mentioned briefly yesterday, but they are experimentally quite difficult to realize. And what I'll talk about today exclusively is propagation-based phase contrast tomography. And so what you do there is very simple experimentally. You just let the wave propagate after passing the sample, and then in free space propagation, the propagated wave, even the absolute value of the propagated wave, depends on the phase information in the exit plane. Okay, let me illustrate this here in this picture. So let's start right away with, I'll start with this sketch of the experimental setup. So, I mean, you can forget for this talk all this. This is just the way that some X-ray point source is generated. All the details are irrelevant for the purpose of this talk. So then the imaging setup is very simple. You just put the sample into the beam and you propagate it. If you want, you can also change the position here. And then you record the diffraction pattern, and the diffraction pattern is, sorry, the absolute value of the electric field. And now, after some simple geometric transform, you can map this point source to some plane wave, which penetrates the sample, and then you have here the exit wave, and this plane here is called the exit plane. In this exit plane, as argued on the previous slide, we have no information on the real part of the sample whatsoever, because it just the real part just gives rise to phase shifts. So this is indicated here. These planes here are the wavefronts, and the wavefronts are a bit tilted, but this you cannot see. So here you can see in the exit plane, you can only see the imaginary part, so the absorption. But then if you solve here, if you let this wave propagate, then at some distance, the diffraction pattern also depends on these things. Yeah. Okay, and then to recover, I mean, here you in the measurement plane, you can also only measure absolute values, and you have to solve some phase retrieval problem. Okay, now this was images. Now let me describe in more detail the mathematical model of this imaging setup. So, I mean, it's very fundamental level. Electromagnetic waves are described by the Maxwell equation in time harmonic form already. And I mean, as is well known, if the gradient, so if n is slowly varying, which for X-rays, which is very small wavelengths, is very well satisfied, then this can be reduced to the Helmholtz equation for the Cartesian components of the electric field. And now in the half plane right to this exit, the half space, sorry, on the right to this exit plane, you can solve this Helmholtz equation. You assume that n is constant, and then you can solve the Helmholtz equation with constant n just by separation of variables. And this is what I did here with some radiation condition. So this is now the formula for the solution of the Helmholtz equation in the right half space. So that great. Okay, now you can do some further simplifications. So you have this square root here in the exponent, and so under the assumption that psi, so the spatial frequencies of the medium that you want to image, are much smaller than the wavelengths. This is an assumption that's also very well satisfied. You can do a Taylor expansion of the square root here, and then you get this model to describe wave propagation, which is called the Fresnel transform. So it's a Fourier multiplier with this kind of sharp function here as a multiplier function. And yeah, you can use Fourier convolution theorem, okay, a bit mathematical trickery, or some arguments, but you can finally apply this, and then this is a convolution operator. And it turns out this operator is the propagation operator of the Schrödinger equation if you interpret, so I mean actually only this operator here without the EIKZ. This is the propagation operator for the Schrödinger equation if you interpret the Z coordinate as a time coordinate. And you can also derive this differently. Okay, maybe let's leave this aside. There are many different ways how to, I mean, it's also many different names per axial equation or one-way approximation to the Helmholtz equation. There are many different derivations of this equation. Okay, so if Z is very small, or actually, I mean, by the way, so that is very large, so the propagation distance is very large, or to put it in, to face it in some dimensionless quantity, the only relevant dimensionless quantity is the so-called Fresnel number, which is defined here. So if the Fresnel number is small, then you can expand the square here in this convolution integral kernel. And if you do this, then you arrive at this expression, and here you have a pure phase vector in front. And if the Fresnel number, so this is what you get from here, if this is very small, then this is almost 0, so you can forget this, and then you get to the Fourier transform. This is basically here the kernel of the Fourier transform. So in this case, what you measure is basically the Fourier transform. In this Fraunhofer regime, the measurements are the absolute value of the Fourier transform. Okay, and so then in order to, first of all, solve the problem to recover the exit wave, we have to solve a standard phase retrieval problem, which means in the near field case that given the absolute value of the Fresnel transform of the exit wave, we would like to find the exit wave. Okay, this is of course as it is highly non-unique because you can, when the Fresnel propagator is a unitary operator, so you can cook up any phase and then apply the adjoint operator, and you get some exit wave, and you get a different one for each phase that you thought of. So in order to solve this, you need prior information on the exit wave. So for example, information on the support, non-negativity, or information on the absolute value. Okay, or in the far field case, the Fraunhofer regime, the phase retrieval problem is given absolute values of the Fourier transform, find the exit wave. Okay, so far we have, this was one part of the modeling. Now we have to describe what is actually the exit wave. So here we do a further approximation. Basically, we assume that the field U can be written as such an exponential, so plane wave propagated in Z direction times a slowly varying envelope. And if we plug this ansatz into the Helmholtz equation, we get this equation here. And then, assuming that this is really a slowly varying envelope, we can neglect the second order derivative in that. That's small. And if we just do that, we get exactly the Fresnel propagator. That's one way to derive the Fresnel propagator. But assuming that the sample is optically thin, we can also neglect additionally this lateral Laplace operator. And if we do that, then we arrive at this model that is typically used in CT. It's the, then you basically get this formula, which I already put in, that the exit wave is given by line integrals over the refractive index squared. Okay, that's called projection approximation. Okay, and then altogether the form, the exit wave is given by that. And now let me illustrate how this looks like. So I've created an exit wave which consists of two letters A and P, and A is an absorption object. So here the imaginary part is non-zero in this letter A region, and here in this letter P region, the real part is non-zero, but the imaginary part is zero. And so then, if delta is we are exactly at the exit wave, then the Fresnel number is infinity, and we can just see the absorption object. If we move a little bit away, we can still see this absorption object very clearly, and then we can see edges of the phase object. If we move further away, so make the Fresnel number smaller, then everything gets a bit blurry. So if we move further away, then at some point we see the Fourier transform of this whole image, and then we cannot recognize anything in the image anymore. So kind of in some way you can say this Fresnel transform interpolates between identity and Fourier transform, but it's not really exactly true, because it only is true if you take the absolute value. Okay, and then the full imaging setup would be described by the following forward operator. You have so it maps a three-dimensional refractive index, which now we additionally rotate the sample in the beam to get additional information, and then we get a radon transform, the forward operator is given by the absolute value of the Fresnel transform applied to the exponential of essentially the radon transform of the refractive index. Okay, and in usual CT, as I said, we just exactly look at the exit wave. So Fresnel number is infinity, and this Fresnel propagator would be zero, would be the identity. And then typically actually would take pointwise logarithm here, and then you just have the radon transform. Okay, so now let's turn to the mathematical analysis of this imaging modality. And to start with is the question of uniqueness. There has been a lot of studies in the Fraunhofer regime, so this classical phase problem for the Fourier transform. It turns out that in the near field regime, the near field regime is much more favorable. There have been early results by Jonas and Lewis on uniqueness if you record two diffraction patterns at different distances. It was believed for some time that with one diffraction pattern it's not possible to uniquely recover a complex valued exit wave. And there was also some counterexample, but then Simon Maretzke could show that actually if you have compact support of the exit wave, which is a reasonable assumption in many cases, then one diffraction pattern suffices. But of course, the next question then is, numerical examples show that often this is extremely unstable. So can we say something about the stability of this problem? And that's the next topic. So we're going to study the stability of the linearized problem, and we linearize around a constant refractive index, constant exit wave. So then, we can expand this absolute value squared, ignore the quadratic term, and the two linear terms gives the real part of the Fresnel transform of U0. So it should be a 0 here. Okay, and then we could show a surprising result, which is that actually the linearized problem in this setting is well posed. So yeah, this is yeah. Usually all inverse problems are ill-posed, but we could show that it is well posed, at least in this setting. So the main assumption here is, besides compactness of the support, that we have an infinite measurement plane, which of course is obviously an idealization. And okay, this is actually the topic then of the next section. But in this idealized setting where we have an infinite measurement plane, we show that the problem is well posed. And actually, I'd like to sketch the proof of this result. So here is again the linearized forward operator, which is yeah, the sum of the Fresnel propagator and the Fresnel propagator complex conjugate. This is immediately, if you look at the form of the Fresnel propagator, or you can also write this as a joint Fresnel propagator applied to the conjugated function. And now what we do is we again apply once more the propagation, the Fresnel propagation operator. And this kind of corresponds to holography. So this TH would be a hologram, and to decipher that, we apply again the Fresnel propagator. And mathematically, what we get here is we get a squared Fresnel propagator plus, since D is unitary, just the signal complex conjugate. And here you can see an illustration of that. So in this diffraction pattern, you cannot really recognize anything. If you again apply the Fresnel propagator, you can see the actual sample that was put in. So this was this logo, and you can read the letters. So you can say nice, but you have a lot of artifacts here. And so now the idea of the, I mean, this would be basically holography. So the idea now of this uniqueness proof is maybe first unintuitive. So we neglect this part here where we can actually really see the true image. And the reason is that we assume H has compact support. This is our main assumption. And this means outside of this support of H, we have the pure squared Fresnel transform. And we don't have this interference with the complex conjugate. And so basically what we have to show is that this is unique and stable. So we have a lower bound for this squared Fresnel transform. And the square Fresnel transform is just Fresnel transform for the half Fresnel number. And here is again the definition of the Fresnel transform. And so the absolute value, this is just here a phase vector. And if we just want to look for the size, then we can also forget this factor here. And then basically we have to prove a lower bound for a restricted Fourier transform. And Fourier transform is isometric. And then basically the norm of this operator here is can be bounded in terms of this operator S, which just maps between two bounded spaces, two spaces on bounded domains. It's quite basically the Fourier transform restricted to these two bounded domains. We have to show that it has operator norm smaller than 1. And yeah, this is actually an easy argument. You just look at the largest singular value and vector. And if this would be really 1, then you would have a function which has compact support both in the spatial and the Fourier domain, and this is of course not possible by analyticity. Okay, so this gives our positiveness. Now we actually want to estimate the size of the inverse in terms of the Fresnel number, and there we considered several cases. The first was that we do not have any further prior information, and in this case, actually the stability constant, so the norm of the inverse operator, increases exponentially with the Fresnel number. And so that's very bad news. And so often we have Fresnel numbers of tens of thousands or hundreds of thousands. And then, of course, this is so huge that practically the problem is non-unique. So extremely unstable. This was also observed by many people, so that's why it was common belief that there is no uniqueness. Yeah, but it depends a lot on the Fresnel, on the size of the Fresnel number. Actually, it is also possible to work at lower Fresnel numbers, which is called deeply holographic regime, and there the problem is much more stable and feasible. So then, okay, this was basically by an analysis of the singular values, which are eigenvalues related to prolate spheroidal wave functions, which were studied in detail in the 60s already by Fabian. So we could use this analysis to derive these bounds here. So then we also considered the case that we have further a priori information, for example, that we image a pure phase object. So the imaginary part is of the refractive index is 0. And in this case, we have a much more favorable stability bound. It does not increase exponentially, but only linearly in F. And here actually the technique of proof was entirely different. When we looked at zeros of the Fourier multiplier and analyzed those. Okay, if we have a so-called a single material object, so we are emitting an object where real and imaginary part are proportional, then we have an even better stability bound, which only increases with the square root of the Fresnel number. And then finally, actually this turns out to be a corollary of this previous points. If we have the situation that we record two diffraction patterns, and actually that's the standard modality, imaging modality that's used, that you record many diffraction patterns at different distances, then we also have just linear increase in Fresnel number. And yeah, we also checked how accurate our upper bounds on stability are, and we found a quite good agreement of our analytical bounds with numerical bounds. So yeah, now as I already said, this analysis that I presented is based on the assumption that we have infinitely large detectors, which is obviously not realistic. And actually, practically, the problem is not so much that you cannot build larger detectors, but you have a finite beam size and also limited spatial coherence. So the area in which the modeling assumption satisfied is bounded. Okay, so now if we look at this more realistic setting, then first of all, it seems pretty hopeless because the kernel of this forward operator, so the forward operator is, as you saw, an integral operator, the linearized forward operator, and the kernel is analytic, which means by the Kuban-Fischer inequality, the kernel can be approximated with exponential rates by polynomials or Méliès wavelets or whatever. So you have singular values which decay exponentially, asymptotically. So, I mean, first we had well-posedness, now we have exponential ill-posedness. Okay, so there seems to be some contradiction. So maybe if the analysis was just completely useless because the assumptions were too idealized. Okay, now first of all, so let's look at this in more detail. And so first, let's consider a physical argument. So let's look at what might be the resolution of this imaging setup. And so if we take the famous Abbé diffraction limit, I mean, it's not really, it's usually derived in the far field setting, so it's not really immediately applicable, but let's apply this nevertheless. So I mean, basically it says the resolution is of the order of the wavelength of the that you use, and actually then also the aperture is relevant. So in this case here we look at some cone, the angle of some cone, where we can still fully record the image here by our square detector here. And so of course this angle depends on the position of X here. And so then this would give this bound here on the resolution. That's the classical version, at least, of the classical Abbé diffraction limit. There is also another argument that leads to that. So now we look again at this Schrödinger picture and interpret the z-axis as time, and we're kind of looking at worst case images where we can see the least. So worst case samples of the exit wave would be such a Gaussian wave packets. They can, I mean, if you propagate them by the Schrödinger equation, they remain Gaussian wave packets and they just travel. And so then you see basically in your window here a Gaussian wave package which is traveling in this direction xi. And so you observe them at some final time. And if the wave package happens to be still in your window, then you have a very easy job to predict where it has been at time 0. But if it has left your observation window, then you observe basically 0, and then you have a very, very hard time to predict what has been there at time 0. And then it turns out, I mean, now you have a finite z, so a finite observation time, or finite time where you have to look back, and it turns out that the propagation speed of such Gaussian wave packets is proportional to the wavelengths here of these waves, and so this kind of gives you, so then the faster the smaller the wavelength, the faster the wave packet moves out, and so this then gives you some bound on the resolution, the size of two heights of these waves in the Gaussian wave packet. And then it's also clear that in the worst case, the Gaussian wave packet moves to the next boundary, and so then you have a smaller resolution near close to the boundary than in the middle. Okay, so these were all heuristic arguments. We could also turn this into a mathematical actually, Simon could turn this into a mathematical theorem, and so he could show stability estimates for finite dimensional subspaces. And more precisely, these finite dimensional subspaces were tensor product spline spaces, so multivariate spline spaces. And then, yeah, he derived complicated bounds on the mesh size, which essentially are very close to this heuristic bounds on the resolution. Okay, so this is kind of then a precise derivation of this form of Abbé's diffraction limit. And it also tells you that, I mean, you get then on just on these finite dimensional subspaces, you get stability bounds which are very similar to the stability bounds which we had for the case of infinite detectors. But it tells you that as long as you don't, if you're happy to just reconstruct the exit wave in this finite dimensional spline space, then you get good stability. If you ask for super resolution, in principle you get it. You can get arbitrarily high resolution, but as soon as you're asking for higher spatial frequencies, then you get very bad stability, and in practice it doesn't work. So basically, this is a better way to look at that. So this argument here in the beginning is, of course, correct, but we basically have a plateau of singular values, and then they decay very rapidly, exponentially. But this is not really the interesting thing, that how fast they eventually decay. The important question is how many large singular values do you have, and what kind of information do they describe. Okay, so then I'll be short on that because I don't have a lot of time left. So we also studied numerical reconstruction methods for the full nonlinear problem. And I mean, actually there's a simple way to solve these problems, which is first to do a phase retrieval algorithm, and then do a radon inversion. So that's fast, but actually the more accurate approach is to do an all-at-once approach and solve the full nonlinear inverse problem. This is more stable because, I mean, the radon transform does not have dense range, and there's this Helgerson-Ludwig conditions, yeah, so then you get additional instability that you also observe. Okay, so we did reconstructions with a Newton-Kaczmarek method, and there we could, yeah, this is the data cube, and this is level surfaces of our reconstruction, and here this was the just a collection of balls, and we could resolve that pretty well with a nanometer resolution. And here is also some image of a cell that we reconstructed. Okay, so now let's come to a discussion of the results. So first here, just a wrap up of the mathematical results that I showed. So I showed uniqueness, I showed about posedness of the linearized problems, explicit stability bounds in terms of Fresnel number, and also I discussed all at once numerical reconstructions. Okay, but I'd also like to talk more about the imaging method itself. So what are opportunities? Why is this an attractive imaging modality? So one thing is that it's scalable. So if you look at these first pictures in Ottmar's talk, actually you can shift the resolution that you would like to achieve with this imaging modality. And so I mean, of course, then you have to make a compromise with the sample size. I mean, but I mean, also if you but that's kind of a very nice feature that you can either run it in a version where you have nanometer resolution, but also in a modality where you can image much larger objects. You have a very large ratio of the sample size and resolution, so you can work with huge data sets. I mean, so far, or initially, people worked with synchrotrons, so then this is kind of difficult experimentally. You only have to apply for beam time at some synchrotron, but also some high throughput desktop devices are under development, so that it can be used for kind of as a standard tool, hopefully in biological biomedical studies. In particular, there's very new and interesting results on so-called virtual histology. That's a talk in its own. I just want to show these very nice results of my collaborator Tim Zaldit here. So here he studied a millimeter cubed area at a resolution. Here you see a zoom of that. I mean, this bar here, sorry, I didn't write it, is 200 micrometers. This scale bar is 50 micrometers. So here you see another zoom in, and so you can see on this millimeter squared a sample, you can still recognize individual cells and the nuclei of these cells. But I must admit that for these size of images, we could not run our nonlinear inversion method. So these were done with a much simpler two-step method. We first do phase retrieval and then radon inversion. Okay, so far the main challenge is high radiation dose. So that's actually also ongoing work. We have new ideas. It's kind of high risk, high gain research, actually in a new CRC that we that just started in January in Göttingen. The idea here is that we fractionate the dose, and we use not perfectly coherent sources, but only partially coherent sources. So then we have, we hope that there is information, additional information in the correlation of the intensities. So we are working with correlation data, and that's very similar to this talk of Maxence Cassier yesterday or Monday. It's a different setup here. So I mean, here we have some preliminary numerical reconstructions where we just show that actually there is really a lot of information only in the correlations of the intensity. So I mean, if you have a perfectly coherent waves and there is no correlations at all, then you have obviously also no information in the correlations. But if you have a partially coherent incident wave, then the correlations of intensities contain enough data to actually reconstruct this object here quite accurately. So there is hope that actually this could lead to a reduction of the dose that's necessary to image such objects. Of course, I mean, you also pay a price. I mean, you have to use a partially coherent beam, so you have some blur in the image. At this point, it's really not clear if this helps eventually if this works basically. Okay, thank you for your attention.